Right, hi everybody, welcome back again. In this one, I want to move on to topic 6. And topic 6 is called Atmospheric Systems and Societies. Obviously, that relates to the Earth's atmosphere and how it plays a role in human society. Topic 6.1, which we'll start today, is called simply the Introduction to the Atmosphere. I'll move on quickly because I want to show you the syllabus statements for topic 6.1. I've just pasted them in here. All right, going through them quickly. So the syllabus says, number one, we need to consider that the atmosphere is predominantly a mixture of nitrogen and oxygen with other gases present. That's referring to the bottom layers of the atmosphere where we live, largely the troposphere. Most reactions connected to living systems occur in those bottom layers, the troposphere, and above it the stratosphere. Largely the troposphere, that's the place where living things largely live. Next, we need to consider that the atmosphere is a dynamic system. It's a system because it has inputs, outputs, flows, and storages, as we've already seen a million times. But it's also dynamic because it changes. It changes in terms of location and in terms of time. We'll give that a little bit of thought. Then we need to consider how human activities impact atmospheric composition, obviously by the way we dump our waste gases into the atmosphere and the effects that has. Now here, I want to be careful here. I don't want to go into too much detail though because there's a lot of crossover with topic 7, which is climate change. So rather than repeat what we say in topic 7, I'll give you links within this video so you can look at the necessary or the pertinent parts of topic 7. Then we need to consider that most clouds form in the troposphere and they play a role in the albedo effect, the natural albedo effect. I'll try and explain that. And then finally, we need to consider that the greenhouse effect is both natural and necessary for maintaining temperatures suitable for life. So the greenhouse effect itself is natural. However, we will cross over to talk about how humans have had an effect on that greenhouse effect and the effects on global temperatures. Again, there's crossover there with topic 7, so I will give you links to go back to topic 7. Okay, so I don't know if it's obvious, but the reason why I changed the layout from the way the IB originally published these points, although I've not changed the content, is because if we look at these points separately, I would suggest the first 2 points here relate to the structure of the atmosphere. And we can think of the atmosphere as having these layers that you can see here. The second 2 points I would suggest are related to why the atmosphere is a system and how we can consider it to be a system, and also the effects that humans have had on that system. And then the final 2 points, the greenhouse effect and the albedo effect. So that's how I want to structure this little talk. The first part, I want to talk about structure of the atmosphere. The second part, why the atmosphere is a system. And the third part will look at the natural greenhouse effect and some of the effects of humans on that greenhouse effect. Okay, moving swiftly on. This is a little pie chart that I've made to show the composition of air. You're probably familiar with this from chemistry lower down in the school. However, we should point out that this is the structure of air in the troposphere, which is the layer of air that goes up to about 10 kilometers in height. Most of the atmosphere here is nitrogen, about 78%. A further 20 to 21% is oxygen, which is obviously very important for life. Carbon dioxide makes up a tiny percentage, about 0.038% by volume. However, it might be small in terms of the amount of carbon dioxide in the atmosphere, but because it's changing and because of human effects, it's having a big effect on the planet. And then finally, there are other small amounts of gases that add up to less than 1% of gases in the atmosphere. Okay. Okay, so the reason why I've put this little picture here is because I remember as a child watching the TV series Cosmos, and in that series, Carl Sagan made a statement that always stuck with me, and he stated that if you're considering what the atmosphere is like, or specifically how thick it is, if you took one of these toy globes, or a fairly large globe that you might have in your living room to represent the Earth, um, in terms of the ratio of the diameter of the Earth to the thickness of the atmosphere, he stated that the atmosphere would be approximately the same thickness as the layer of varnish on the outside of that wooden globe. It always stuck with me. I don't think he's quite correct, because I think technically, with more understanding of the atmosphere, we know it extends quite far out into space. The difference between the layer of varnish on the globe and the atmosphere itself is that the layer of varnish is the same thickness, whereas the atmosphere gets thinner and thinner and thinner as you go further away from the Earth. However, I think the point stands that he was making is that the atmosphere is very, very thin in terms of the ratio of the Earth, and it's a very precious commodity. And we shouldn't just treat it as we do, as an open sewer to dump our gaseous wastes. Okay, so in terms of structure, the atmosphere is a mixture of solids, liquids, and gases. It's held in place by the Earth's gravity. The first 10 kilometres we could think about as the most important layer, certainly for our needs, because it's where we live and it contains the air that we breathe. It's called the troposphere. It's also the layer where all of the Earth's weather and cloud systems occur. And above that is another layer which goes up from about 10 kilometres to 50 kilometres, which is called the stratosphere. The stratosphere is where the ozone layer exists, which we'll talk about later in topic 6. And it's also the layer where we have commercial jet aircraft fly. And the reason they fly in that area is because the air is thin, less air resistance, and less turbulence. And it means that planes don't need to fly through cloud systems there. Okay, so those are possibly the two most important layers. Here's a kind of map of those layers and other layers. So as I said, the first 10 kilometres is the troposphere, approximately 10 kilometres. That's about the same height as Mount Everest. I've put in there for scale. Above the troposphere, between about 10 and 50 kilometres, is the stratosphere, where the ozone layer is located. Above the stratosphere is the mesosphere. Above the mesosphere, the thermosphere. It probably extends further than 120 kilometres, as you can see here. And above the thermosphere is the exosphere, which extends out into space. The thermosphere, by the way, is the layer in which we have orbits of satellites, including the International Space Station, that orbits within the thermosphere. The thermosphere is also referred to very often as the ionosphere. It's where there's interactions with solar energy that ionizes the gases in this layer. Okay, moving on again. These are the layers, again, troposphere, from the word tropine, to mix. Stratosphere, from the word stratus, which means spreading out. Mesosphere, meaning the middle layer. Thermosphere, the heat layer. And exosphere, the outer layer or the boundary with space. And although that's probably extends a few hundred kilometres out into above the surface of the Earth, life or the biosphere is restricted to the innermost 10 kilometres, which is the troposphere. Okay, the troposphere contains most of the mass of gases in the atmosphere, and for that reason, it's where clouds form. Now, in the opening part of this little talk, we mentioned the albedo effect, and you should already know what that is from other parts of the course. A white layer is very reflective in nature, and therefore white clouds are also reflective in nature. Some clouds are more reflected than others, so therefore we say some clouds have a bigger albedo effect than the others. The albedo effect is the natural reflective effect of a white surface. So that could be ice and snow on the surface, or it could be the white surface of clouds. So if we change the cloud systems in our atmosphere, we change the albedo effect also. We already talked about albedo effect as a positive feedback effect in topic 7.2, and I'll put a link there where you can see that. Okay, and then we need to talk a little bit about the atmosphere as a system. So the atmosphere has inputs. It's an open system, so therefore has inputs of energy and matter. Inputs of solar energy, obviously. Inputs of space debris, meteorites. Outputs of reflective solar energy. And outputs of dust and other gases that float off from the atmosphere. And also in the last 60 years, output of spacecraft and satellites that humans have deliberately allowed to leave the atmosphere. It's dynamic in nature because it's, as I've said, it's changed over location and time. It also changes in terms of altitude. In terms of time, you might not know this, but there have been big changes in atmospheric composition over time. So this little graphic goes back 800 million years, and it encompasses the three main eras of Earth's geological history. In pink, we can see going back from about 250 million years to 800 million years, the Paleozoic era. Zoic meaning life and paleo meaning ancient. So this is the era of ancient life. The orange layer is the Mesozoic Mesozoic era, which is the middle age of life, or commonly probably known as the time of the dinosaurs. And then the Cenozoic era, where we're living, in which we're living at the moment, which refers to modern life. You can see that the blue line represents global temperatures, and the red line represents the amount of carbon dioxide in the atmosphere. There's a link between them. So you can see that this is the approximate temperature now. Average global temperatures are somewhere between 12 and 15 degrees Celsius. It was much hotter in the past, certainly in the Paleozoic era, with these dips. These dips represent ice ages. The last ice age was approximately 12,000 years ago. We're probably due for a new ice age within the next 100,000 years or so. And you can see that carbon dioxide concentrations are very high, certainly in the Paleozoic era. We can put that down to volcanic activity. You can also see, I don't know if it's visible on this graph, a huge rise in global temperatures predicted over the next few years if we allow climate change to continue, human-made climate change. Okay, so that's representative of why the system is dynamic in nature, in terms of its composition and in terms of its temperature. Right, and then finally, to finish this video, just a few words about the greenhouse effect. I will put a link to topic 7 here, so I don't want to repeat too much. But in terms of the natural greenhouse effect, it works because solar energy is released by the sun. It's high energy, low wavelength waves, which comes down from the sun, hits the Earth's surface. Some of the energy is absorbed and it's reflected with longer wavelengths. Those longer wavelengths find it much more difficult to move through the atmosphere, and although some is lost, some is reflected back, and that keeps the average temperature of the Earth at about 15 degrees C, which is what is needed for life to exist within the troposphere. Without this greenhouse effect, without this natural reflection of solar energy backwards from the atmosphere, global temperatures would be on average about minus 15 degrees Celsius, in which case life couldn't exist, or certainly life as we know it today. On this graphic as well, you'll also see the effect of cloud systems, and that's representing the albedo effect of these white surfaces of clouds. We could talk a little bit more about how humans are affecting this system, but rather than do that, I'll give you a link back to topic 7, as I said before. Okay, I rambled a little bit, but I hope that was helpful. And I hope if you go back over this stuff, you can see that we covered, number 1, the structure of the atmosphere in terms of its layers and its composition. Number 2, why we can refer to the atmosphere as a system. And number 3, the natural greenhouse effect of the atmosphere, including the albedo effect of cloud systems. Right, okay, thanks for your attention, everybody. We'll watch this in our classroom and we'll discuss it there. Take care of yourselves and your family, and I will speak to you this week.